So this reminds me a little of I'll make a variant of it, of the Jewish joke. If I were Rothschild, I would be richer than Rothschild, because I would have all of those millions, and I'd have a lecture on finite groups and modular forms as well. This is wrong. So now the people on video have missed an excellent joke. I promise to make more. I don't promise to be comprehensible, but I do promise some occasional jokes because I can't resist them. So I, in real time, 10 minutes ago, decided to reverse the order of the lecture. The title is From Modular Forms to Finite Groups, but I'll go the other way. I was told that this should be a very general lecture, that maybe some students, but there aren't any because it's vacation, from the university might come, or at least it should be very generally understandable. So if anybody doesn't understand anything at any point, I have failed. I hope that hasn't happened yet, at least. Okay, so I'm also going to take this thing off because you've seen it now. Okay, so I'll start. I'm going to, there are two ingredients in the title, and I'm going to pretend, even though I don't necessarily think that's the case, that no one here knows what either one is. And so I'm going to give a mini course on finite groups and their representations, and another mini course on modular forms, so that no one will feel left out, and those who know, which is pretty much everybody, will be comfortable and relaxed. Okay, so as I said, my title was From Modular Forms to Finite Groups, but I'll go the other way. Finite groups are certainly better known in mathematics, more pervasive, and also they're easier, at least at the level of what I'm going to say. They're much, much harder as a theory. So G is a finite group. I'm not going to tell you what a group is. And so I remind you what a representation of this group is. It's a vector space over C, the complex numbers, on which the group acts. So for each G in G, this gives you a map, a linear map from V to V. So if you wish, if you choose a basis, it's simply a matrix, and the product of two G's goes to the product of the corresponding matrices. So for instance, the identity matrix, the identity element of the group goes to the identity matrix. And it's called irreducible. Well, this isn't actually the definition, but a fact. But if it's not the sum of two smaller pieces, two smaller dimensional representations on which G acts separately. And so the basic theorems, the basic facts, are that there are finitely many, only finitely many irreducible representations. Let's say V1 up to Vm. So let's fix the order of the group. Let's call it, not fix, but denote it by something. V1 up to Vm, up to isomorphism, of course. And there are two more precise theorems which make that more precise. To say that M is finite, well, it's better to give a formula for it. M is exactly the number of conjugacy classes in the group G. So two elements are conjugate if one is G and the other is some A, G, A inverse for some other element of the group. And so you count the classes, and there are usually far fewer classes than the size of the group. We'll see an example in a moment. And so that's certainly a finite number, so it shows that it's finite. And another famous formula, these are all very easy to prove, the very beginning of the theory, is that the sum of the squares of the dimensions of these representations, so each one is finite dimensional, that's also a theorem, and the sum of the squares of their dimensions is n. So let me give an example here, and then I'll introduce a little more terminology here and add it to the example. So the simplest non-trivial example, I'll take the smallest non-abelian group, which is S3, permutations of the numbers 1, 2, and 3. So there are three conjugacy classes. So that means in the notation I already introduced, M is 3. One of them is the identity, which fixes 1, fixes 2, and fixes 3. One is, I'll always use T for the transposition. It interchanges two numbers, let's say 1 and 2, and it therefore, of necessity, fixes the third. And finally, Z, or Z, sort of a German abbreviation, is the cyclic permutation 1, 2, 3, which sends 1 to 2, 2 to 3, and 3 to 1. So there are, so these are the conjugacy class. Well, these are representatives. So it's really I is the class of this. So this is the conjugate class And the size of C, well, there's only one identity. Anything conjugate to the identity is the identity. But here you can fix either 1 or 2 or 3 and interchange the two others. So there are 3 elements like this and 2 like this. And of course, it adds up to 6, which is 3 factorial, which is the n in this case. This is a group of order 6. OK, so therefore, there are also 3 representations. I won't define them, but I'll give the numerical data in a second. Namely, if V is an irreducible representation, and if C is a conjugacy class, and remember there are equally many of these, then I'm going to define a number. And since there are equally many, I'm going to define a square matrix. But actually, I'm going to define 2 numbers. And one is familiar to anybody who's had any kind of a course in group theory, but the other is surprisingly less familiar. So one of them is called chi V of C. And it's simply the following. You take any element in this given conjugacy class. They're all conjugate. Each G acts on V as a matrix of a finite size. So it has a trace. Conjugate matrices have the same traces, so this trace only depends on the conjugacy class. So that's one, and since I've m irreducible representations and m conjugacy classes, that gives me a square matrix, which is known to be invertible, at least over C, let's say. But there's another thing you can do. I'll call it nu. There are various notations, which, well, first I'll just give a formula for it in terms of the first thing. You take the size of the conjugacy class. I mean, it's the same as before. It's chi V of C, but you simply rescale it. You multiply by the size of the conjugacy class, but then to make up for it, you divide by the dimension of the representation. And so I'll tell you what this is. It's simply the following. You take all G in the given conjugacy class, and each one is a matrix. When you act on V, it's just a matrix, a square matrix of a given size. When you add them up, it's still a square matrix, but that square matrix now commutes with everything in the group, because if you act with A, then since the G just gets conjugated, and I'm summing over everything. And so Schur's lemma tells you that this thing is a scalar multiple of the identity. If you don't know Schur's lemma, then you just learned it in this case. So this sum of matrices is simply going to be a scalar number, a number, times the identity matrix, 1, 1, 1, 1, and otherwise zeros. And that number is called nu V of C, and it's an easy check that this is true. So let me give you an example. So I'm going to make a little table. So here's C, I, T, Z. Here's the size of C, 1, 3, and 2. And then there are 3. Well, so here M was 3. N was 6. So therefore, I should have 3 V's, and indeed I do. So which way did I make my notation? The V is in the denominator. So I'll give you first a table of the 3 characters, as they're called. These chi's are called the characters, and the others, I think, are nameless. So it'll be nu V1 of C, nu V2 of C, nu V3 of C. So the table, I better look at my notes, because to try to do this without getting confused won't work. So the trace of the identity, of course, is just the size of the matrix. So it's the dimension. So in particular, it's always a positive integer. By the way, for all symmetric groups, I'll use that later, you get integers for both the chi's and the nu's. So the dimensions are 1, 1, and 2. And you see, indeed, that 1 squared plus 1 squared plus 2 squared equals 3 factorial. As I promised you, that the sum of the squares would be the order of the group. Then the next one is 1, minus 1, and 0 for this representation. And the last one is 1, 1, minus 1. Those are the characters. So now if we apply this recipe, I have to multiply by the size of the conjugacy class, which is 1, and then divide by the dimension, which is this. So the first row is always 1, 1, 1. Here I have to multiply these numbers by 3. That's the size of C, and divide by the dimension. I get 3 over 1, minus 3 over 1, and luckily 0, because 3 is not divisible by 2, but 0 is. And then here I multiply by 2, multiply by 2. Here I multiply by 2, but I divide by 2. So this is the other table. So we have these 2 competing tables, and there are lots of nice relations. So now a remark is that G, let me get it right, M, which is the number of conjugacy classes, and therefore also of representations, is usually much smaller than N. In my example, they were 6 and 3, so that wasn't really much smaller. But in general, it is. So I'll give you 2 examples. If I take G to be the symmetric group on n letters, then n is n factorial, and n is what's called P of n, the number of partitions. So a partition, well, you can see it here in this table. Here I partitioned 3 into 3 pieces of size 1, 1, and 1. Here I partitioned into pieces of size 2 and 1. And the last one, which I've erased, I partitioned into a single piece. So a partition of numbers is a splitting up, regardless of the order, of n into positive integers. And each one of those corresponds in the obvious way to a conjugacy class, because this just means each conjugacy class in Sn is a product of cycles. And so you have here one cycle of length 2 and one cycle of length 1. So I have a 2 and a 1. So in that case, this is the number of partitions. And now the growth of this one is asymptotically equal to the square root of 2 pi n times n over e to the n. This is Stirling's formula. So it grows more than exponentially. It grows more than like a constant to the power n. But this one is like 1 over 4n squared of 3 times e to the pi square root of 2n over 3. This is Hardy and Ramanujan. And so it grows much more slowly. It only grows exponentially in the square root of n. So indeed, we have a very big number. Well, they're both very big, but this is very bigger. Let me give you a little table just for fun. I'm going to actually use these in a moment. Well, using is exaggeration. I'll even define it for 0, although I haven't really made much sense of that. So the number of partitions is 1, 1, 2. We just saw there are 3 here. Here there are 5. I'll let you count them. It's very easy to do. And just as an example, if you take 2 million, then you get, uh-oh. Three nine nine. Where the heck did I put it? 3972. Oh, it's not that big. Okay. Okay. It's actually no. Now it's correct actually. Okay. So much for trying to learn a number by heart quickly before the lecture to impress you with my memory. Okay, so you see it grows very quickly, but still 200 factorial would be a lot bigger. And an even a more striking example, as I'm sure everybody knows, there is a thing called a simple group, a group that has no normal subgroups, and they've been classified, probably, and there are various families, some infinite and so on, but there are 26 sporadic groups, and the biggest sporadic group is called the monster, sometimes called the Fisher-Grease monster, after the people who more or less showed that it existed. Sometimes called the friendly giant, with the same F and G. And this thing has the rather large orders. In this case, n, the order of the group, is 2 to the 46. This I didn't even try to learn by heart. 2 to the 46 times 3 to the 20 times 5 to the 9 times 7 to the 6 times 11 squared times 13 cubed times 17 times 19 times 23. These are all primes, but that's not an accident. I'm giving you the prime factorization. Actually, they're very special primes, and that is an accident. I'll come to that later. So that number, as you can see in your head, is about 8.08 times 10 to the 53, which is fairly big by usual human standards. And n here is 194, which is a lot smaller. So this is just to give you some general picture of how group theory of finite groups looks. So now let's come back to, I want to maybe keep this table. Can I ever get that back? Oh, wait. I just figured it out. Sorry. See, I'm not as dumb as I look. Okay. So I just showed you that P of n grows very fast. So you might want to compute P of n. And this was done by Euler in the 18th century. Insofar as I know, this is the first example of a generating function ever written down. Let me change that to a Q. It somehow looks better to people like me. He noticed that just essentially by the definition of P of Q, you can factor the generating function. So this is the generating function. I think this is the first generating function ever written down in history. So he realized that the right way to count these numbers is by taking a power series whose coefficients are the numbers P of n. And then he noticed this factorization, which is sort of obvious, because if you think of the geometric series, for instance, 1 over 1 minus q is 1 plus q to the 1 plus q to the 2 plus q to the 3. This is 1 plus q to the 2 plus q to the 4 plus q to the 6. So it's the multiples of 2. this the multiples of 3. And so if you pick out the coefficient of q to the n, you're just writing n as a certain number of 1s, a certain number of 2s, a certain number of 3s, and so on. That's a partition. So this was his thing. So he noticed that, but that doesn't help you very much to compute this number. By the way, I didn't say this number was computed by Major McMahon. I won't write it down. But in 1917, which in particular means by hand. So that's quite amazing. He didn't sit down and count all of those partitions. So he used a formula Euler discovered. Namely, Euler had the following really brilliant idea. Well, he was Euler, so it was easy. He said, let's look at the product where I don't take the reciprocal. After all, that's much more natural, even though I don't need it yet. And if I can recognize what that thing is, then I get some other power series, and then it's easy to invert a power series. That just gives you some very simple recursion for the original coefficients. So he did this, and what he found, to his amazement, and it's still kind of amazing, is that when you do this, almost all of the coefficients are 0. I mean, I've just given you all the coefficients up to 22, and there are only a handful that aren't 0. And the coefficients that aren't 0 are always 1 or minus 1. And so what he found, but it was empirical, is the sum, he wrote it slightly more complicated way, q to the power 3r squared plus r over 2. So he found this amazing formula. It took him, by the way, 10 years to prove it. But why? So question. Why is this true? Why is such a formula true? I mean, how does one prove such an incredibly difficult formula? And the answer is, of course, modular forms. So modular forms, which I'll now turn to, are a wonderful class of functions. They're absolutely central in modern number theory. Well, for me, they're absolutely central in everything. Everything I do is somehow connected with modular forms, but in some sense, that's true of a big part of modern number theory. And at the elementary level I'll be talking today, they're just power series in a variable usually called q, which are very, very restricted. There are very few of them, but we have complete control over how many there are. And therefore, if you have a conjectural identity, like you've noticed that this series seems to, or this product seems to be equal to that, what you have to show is this is a modular form, and that's a modular form, and then the definition of modular forms is so restrictive that if two modular forms, if the first few coefficients and their expansion agree, here you only need 1 and Euler gave us 50, then they're already equal. So there's a principle that if two modular forms are known, if two functions are known to be modular forms, and they're equal up to a certain point, which is effectively known how far you have to go, then they're really equal. This, by the way, was the essence of what had to be proved by Andrew Wiles for his proof of Fermat's theorem. It had already been reduced to showing something like an equality of modular forms in a very sophisticated sense. But I mean, just to say that this is a deep principle and not that easy. So I won't give you examples. So I now start, and the talk is going to have 3 parts. Well, it's already at 1 on groups, but I mean the modular forms part. I'm going to talk about classical modular forms, and since I'm lazy, modular forms will now be MF from now on. Then there's a generalization which is very easy. And again, I'm not going to tell you any of the theory, just a basic, how to write down some. And then there's an even worse generalization, also very beautiful, which basically goes back to the Mach theta functions of Ramanujan in his famous letter to Hardy in 1920. And so you have more and more difficult types of modular forms, which I'll try to go easy on the definitions. But each one of these classes is going to have a remarkable connection with finite group theory. So, well, we've actually already seen one, because I've already told you that this thing is a modular form, or very nearly. So let me give you a couple of other examples. I prefer to work with examples than with the too many abstract definitions. So let me write down some examples. So the first example is very amusing for the experts. Because they all know that this is an example of not being a modular form. So it's not much of an example. However, we'll need it anyway. It is, however, a quasi-modular form, and it's actually also a multi-modular form as it happens, although that's completely exceptional. But I've already introduced there's an index 2, which doesn't mean anything yet, but a modular form has a weight. So if a modular form has a weight, which is usually an integer, sometimes a half integer. You'll see examples of both in a moment. And if you have another one of k prime, then f times g will have weight k plus k prime. So you can add and multiply these things. They form a graded ring. And this is not quite a modular form. It's very near, but it's got weight 2. But you can go on. So you do the same thing with n cubed. So this is 1 plus 240 q plus 2160 q squared, and so on. So that's a nice example. And you have E6. I don't know why I'm doing this. I want to give you another example first because it's prettier, but now I've started, so I have to continue. So n to the 5th, q to the n over 1 minus q to the n. I'll spare you the thing. And more generally, but actually I want a slightly different normalization. For each k, in a positive even number, you have a certain number, which I'll write it down in case you, for those who like Bernoulli numbers, it's the Bernoulli number over minus 2k. But the important part is the thing that you can already guess, because I gave 3 examples. And so the theorem is that whatever modular forms are, this thing is a modular form of weight k. You can easily see, I haven't told you what this number is, but believe me, it's correct that these are multiples of G2, G4, and G6. All of these GKs, except for G2, are modular forms, and in fact, it's even better. They're known to be polynomials in E4 and D6. But that's completely amazing if you think about it. So if I start, well, G4, of course, thank you for nothing. It's just 1 over 240. E4, it's defined by the same formula. And similarly, G6 is minus 1 over 504 times E6. That's no big deal. But G8, by the theorem, has to be a polynomial in E4 and D6. And since it is degree 8, the only polynomial of that degree is E4 squared. And so you get a totally amazing identity, which when you multiply it out, it's true on your computer, and you don't know why, and you never will know why that's not true. There is an elementary proof, but it's much harder. But the easy proof is because they're modular forms of weight 8, and the definition that I haven't given you is so restrictive that one coefficient is enough, and the leading coefficient is 1 over 480. So that's the end of the story. Similarly, G10 is 1 over 264 with the minus sign times E4, E6. And G12, if I remember correctly, but I think I don't, I'll look it up in a second, it's 440 plus 200 and, well, that's up to 691. 251? That doesn't look right at all. 441, that's the number that factors. 441 is 21 squared. And then 250 also factors very nicely, and they still add up to 691. Not that you know, if you're not an expert, why I want 691 there. This is very nice, but it's not mine. But I'll take something which is, it's 65,520, which factors into 2, 3, 5, 7, and 13 with various powers. Okay, so you have that rather remarkable fact, but it goes on, and as I say, the reason is that these things are all modular forms whose weight is the index I told you, and then there's this theorem that every modular form in this context is a polynomial in E4 and D6, and so these formulas are forced on you. Here, those two coefficients, you only have to look at the coefficients of 1 and q to determine them, and then you get all the rest for free. And that's the marvel of modular forms and why identities like Euler's become so easy. Let me give you a more interesting example. I take the 24th power of Euler's function. So Euler's function, or rather after he took the reciprocal of his original one, was the product 1 minus q to the n. And so I take it to the 24th power, and I multiply by q. You'll see why in a minute. I claim that's much nicer. So let's look at the first few coefficients of these. These I don't have to look up. Plus 4,830. I don't care very much about that one. But then I come back on the line minus 6,048, q to the 6th, and so on. So if you're Ramanujan, which probably is not the case for anyone in this room, then you immediately notice that this number, minus 1472, is the square of that number, which is a beautiful multiplicativity. 4 is 2 times 2, and lo and behold, minus 1472 is minus 24 squared, except that it's slightly off. You have to subtract 2 to the 11th. But Ramanujan noticed that kind of thing just right away. But he also noticed that the coefficient for q to the 6th, you see 6 is 2 times 3, and 2 and 3 being co-prime don't interfere with each other nearly as much. And so this number really is minus 24 times 252. And so he found this wonderful multiplicativity. He discovered it in 1916. It was proved in 1917 by Mordell, showing the power of British mathematics. And that was the beginning of what's now called the theory of Hecke operators, invented not by Hecke and not even by Mordell, but by Horvitz half a century earlier, but sort of came to life with this discovery. But on the other hand, it turns out that this is, I'll now use a notation, this is a modular form of weight 12, so by our theorem that I already had, it has to be a polynomial in E4 and E6, and because the weight is 12, it can only be a linear combination of E4 and cubed and E6 squared. And so you find this, and again, this is an identity which would be incredibly hard to prove directly. But if you know this is a modular form, of course, I haven't even told you what they are, let alone how you check that this is one. But if you know that, then you get this for free. So that's the magic of modular forms. And so I want to combine the magic of modular forms with the mystery of finite groups. So let's start with this. So let's look, as I promised you, at Euler's formula. And let's write it more intelligently. I'm sorry, that sounds very rude, that I want to write it more intelligently than Euler.
24 squared is 576, so how do you get 1400 something?
Because you subtract 2 to the 11, which is 2048, and that makes it negative.
11.
2 to the 11, that makes it negative, and it makes it just right.
Okay.
Take my word for it.
Okay.
I checked it on the computer just 10 minutes ago. It's really true. Okay, I also was worried about that briefly, but then I saw that everything was going to be all right. Okay, so let me come to Euler's identity. So let me define a function called eta of q if you wish, which I'll simply take the 24th root of delta to get back to what Euler originally had. But now you notice, well, you notice because I've told you that these are modular forms and that modular forms are good things. This had weight 12, and the weight is multiplicative, so this has weight a half, because I've taken the 24th root of something of weight 12. But this had an extra q, and you notice it was crucial. Without that q, everything would have been shifted by 1. The multiplicativity wouldn't have worked. So we know from the theory of modular forms that it's crucial to put that, and that's what Euler missed, because then it's just what you learn in school about computing a square. This funny 3r squared plus r over 2, if you add a 24th to it, is much nicer. Up to a constant 24, it becomes a perfect square. 6r plus 1 squared over 24. So that's actually the proof, because this thing is known to be modular of weight a half by those identities, or by, actually there are many, many, many proofs of that. And this is what's called the theta series. So any series like this, where you have q to a perfect square, but it has to be a perfect square, no fooling around with inhomogeneous terms, has to be really a square. This is the theta series, and such a thing is always a modular form of weight a half. If there's one variable, if I had several variables, it would be 1/2 the number of variables. If I had, for instance, q to the a squared plus b squared. So that's a big class of modular forms. Now, I can tell you the definition of a modular form for those who don't know it. You see, when I say that this is a modular form, or when I say that delta is a modular form, let me change notation. You should really think of it as a function of a secret variable z, and so I have to call it tau, and you write q to be e to the 2 pi I tau. Of course, that hasn't done anything. You can make that substitution for any function of q. But now this function has two amazing properties. One isn't amazing at all, but the other is. The first is that it's invariant under sending tau to tau plus 1. Well, of course, e to the 2 pi I is 1 by Euler. But what's completely amazing, and not easy to prove, although there are now many, many proofs, and it's considered easy, is that delta also is invariant, well, up to this factor, under sending tau to minus 1 over tau. And now it's known that those two transformations generate the whole group called SL2Z. So that means that for all matrices A, B, C, D in SL2Z, this definition maybe I won't recall, it just means it's a 2 by 2 matrix with integer entries and determinant 1. For all such things, any such transformation, these are special cases for the special matrices 1, 1, 0, 1, and 0, 1, minus 1, 1, 0, but they generate all of these, and so you get a general theorem that for all modular transformations, A, B, C, D, like that, that you have this invariance property. And that's what being a modular form really means. But it's hidden, because what you see with your naked eyes is only the Q expansion. And in the Q expansion, you can never see what happens when tau goes to minus 1 over tau, because it changes Q into some random other Q. So you can never see it, and it was only when people realized in the 19th century, it started actually with the work of Gauss in some sense, that you had to think of it as a function of the log of Q, that these wonderful properties became evident. Okay, now I want to, that's enough for my summary of classical modular forms. Now I want to give you the first amazing connection. Of course, this one is very famous and almost everyone has heard of it. It's the two newer ones, which I mentioned in my abstract, and that I really want to get to. But I'll talk about the first. So we had the monster group before, and I told you that for that group, M was only 194. There were only 194 conjugacy classes, but N was about 8 times 10 to the 53, so it was absolutely huge, but only 194 conjugacy classes. So here I can make a table, and I mean, remember I made that character table before. I'm conjugating it because the board is turned that way. The first row, which is, oh no, it's still the first row, is just the dimensions. So I'm just going to put the dimension of VI. So I will be 1, 2, 3, and in principle up to 194, but I'm not going to give you, but it would be only a list of 194. Even though the group is so big, there are relatively few conjugacy classes. And the dimensions are as follows. Well, there's one representation that every group has. You can just take a one-dimensional space, C, and the group doesn't do anything to it. It just sends every element to itself. Each G acts as the identity matrix. That's the trivial representation. You always have it. So that's no surprise. But since this group is big, remember we have only 194 numbers. And the sum of their squares has to be 10 to the 53. So at least one of them has to be big. Well, actually, they start right away. After the 1, the very next one is 196,883. And the one after that is 212,96876. And the one after that, I don't have my notes. And I want to emphasize these are numbers which group theorists just knew. I mean, good people in finite group theory at the time I'm talking about, which would be the late 70s, knew these numbers. They'd seen them. This is a 6 and not an 8. But the multiforms people knew other numbers, and there was only one person who knew both groups and noticed something. So in multiform theory, you don't just look at multiforms, you also look at what are called modular functions, which have weight 0. So they're quotients of two things of the same weight. And so the basic one is what's called the J function. It's E4 cubed over delta. So remember, I gave you the beginning of the expansion. You take that thing and cube it, and you divide by q minus 24q squared plus 252 q cubed, and so on. And when you do this, what you find is it starts q inverse. Then there's a term which turns out to have no particular meaning. It has a little bit, but let's forget it. It's actually 3 times the dimension of E8. But then the next coefficient, which every number theorist knew, just they didn't know those numbers, is this. Now, you don't have to be very observant if I put them next to each other like that to notice that something is happening. But only John Mackay actually noticed this, because I say the people, I mean, I was certainly one of them. To whom this was, I could have said that number by heart. And many of my friends could have. And other of my friends, but that I didn't talk to about mathematics, could have said the other numbers by heart, but they weren't the same people. And so also the next one is, so the next coefficient is like this. So those are the first few coefficients. And you see, this isn't quite the dimension of the smallest irreducible representation, but it's 1 plus that. And similarly, what is it, 21,493,760 is not quite this. But if you look, if you see that it's very close. And so that certainly suggests, once you've noticed this, that you should subtract that and see what's left. And then if you do that, guess what? You find 196,884, which you've already cleverly recognized as 196,883 plus 1. And so, you get this nice form. Then it continues like that for a while. Of course, after a while, it doesn't make much sense. Because if you keep going on, when you take the coefficient of q to the 1,000, it's some gigantic number. And of course, you can write any gigantic number as the sum of any 194 given relatively less gigantic numbers. So you have to make sense of this. And that was finally done. This was the famous moonshine conjecture. I won't go into the whole story, but it was finally done by Borchertz in, I think, 1992, and got him the Fields Medal. So this is our first serious and very, very deep connection between multiforms and finite groups. But it's a very, well, by now, pretty old one, and very familiar. So I wanted in today's lecture, after this very long introduction, to tell you 2 other cases, if I can find the thing for pulling down, 2 other cases that come up. So I've now done some tiny amount of my notes here. Okay, so I now continue to quasi-modular forms. And I'll actually even give you the definition, but you don't really need the definition, because I'll give you a structure theorem which tells you what they all are, and then that you can just take that as a definition if you want. But I can't give it to you. So now I want to get my notes. So quasi-modular forms. This is now the second part. The first part was classical modular forms, and that led to the monstrous moonshine, the connection of the representation theory of the monster group. Now I talk about quasi-modular forms. Well, we already had E2, E4, E6, and so on. Well, I mean, I call them G in another normalization. This one, these were all modular, and this one isn't, but it is, as I already said, in fact, a quasi-modular form. By the way, you can see something if I write prime for as the d by d tau, but that's very unpleasant because every time I differentiate e to the 2 pi I n tau, I'll pick up a 2 pi I. So let me just define prime as renormalized d by d tau, so that's the same as differentiating in q and multiplying by q. Then you can see very easily that E2 is nothing else than delta prime over delta, which is the same also. This is the logarithmic derivative, and delta is the 24th power of eta. So of course it's 24 times eta prime over eta. So E2 may not be modular, but it's very close. It's just the derivative of a modular form divided by that modular form. And so there's an intrinsic definition. So I will give the definition, but I'll put it in parentheses. So if this is not your cup of tea, then just switch off for half a minute and then switch back on or have some tea. So, but the actual definition is this. A quasi-modular form is a function which is not modular, but it can be completed in some very simple way. And here, the completion is you subtract a constant over y. The constant is 3 over pi. Y is the imaginary part of tau. So this function is now no longer holomorphic. It has this unpleasant imaginary part, but it's extremely simple. And now this thing does transform, does behave correctly. In other words, it transforms exactly the way that I wrote before for modular forms. It just is no longer a holomorphic function. It no longer has a Q expansion. This part is a power series of Q, and then there's this extra piece. And more generally, you have quasi-modular forms of weight K, and a typical function of that would be a holomorphic function. So it will have some expansion in Q, but what happens is that it's a completion, and the completion will be f of tau plus some f1 of tau over y plus up to some fr of tau over y to the r. It's going to be a polynomial in 1 over the imaginary part of tau, where each of the coefficients is a power series in Q, and the whole thing transforms correctly. Okay, end of the parentheses. Please ignore this if you haven't seen, but just you can see that it's not, this isn't black magic. It's just a relatively simple definition that takes getting used to. But anyway, as I said, you don't need it, because the theorem is, in this case, if you take all quasi-modular forms, the tilde is here, you take just the direct sum, then just as modular forms were generated by E4 and D6, now they form a ring, and they're generated by E2, E4, and D6. And what's more, this ring, for what it's worth, which is kind of important, is closed under differentiation. So for instance, E2 prime is 1/12 of E2 squared minus E4, and so on. So that's a wonderful ring. We didn't have that property before. So these quasi-modular forms, although the definition is a little trickier, are higher. And just to, well, I'll leave it at that. So now I want to tell you a connection of this with group theory, but before it's group theory, it's going to be a little bit of topology. So let me see that I'm not missing anything. Let me define n of g n as the, well, I'll put 0 for connected. It's the number of coverings. Well, the number, there's a little bit of, you have to count correctly. So you have to count up to isomorphism, and then if something is automorph, you have to divide by the number of automorphisms. So although I'm counting something, it's actually sometimes a rational number. I'll give you examples in a second. But it's the number of coverings where you have a surface of genus G, so something with G holes. So here G would be 3. And downstairs, you have a torus, so G is 1. Genus 1. It's not the same G, of course. So in the example, G is 3. And then you have a map, which is n to 1. In other words, it's a many-sheeted covering over every sheet here. You have n sheets above it. But there will be some ramification points where 2 sheets come together. If you've never seen this, which is not the case, of course, for experienced number theorists and algebraic geometers, but if there are younger people in the audience, which I doubt, if you haven't seen it, just forget it. You have to work out what this means. Remember that since this is a surface, I've drawn it as a line, but here really, this is a complex plane, and what I mean here is locally, it looks like mapping the complex plane to itself, by sending z to z squared. And then every point has two inverse images except the origin, which is only one. And that's all it means. Okay, so this is that's called a ramified covering, but I'm assuming the simplest kind of ramification, which means that at every point where there are fewer than n points above it, there are exactly n minus 1. So two sheets come together, but nothing worse happens. So this is, and you can also let n be the same, but not necessarily connected. So in other words, I could have several Riemann surfaces mapping down with the total degree is n, and the sum of the Euler characteristics is 2 minus 2g. Don't worry about it, but I have to say it because I'm going to need it in a second. So this was somehow worked out by the physicists, in particular by Dijkgraaf, what it should be in terms of group theory, or what it is in terms of group theory. That part is completely rigorous, and then they analyzed that, in particular Dijkgraaf and also Rudd, don't know, and found that you get some quasi-modular forms. So let me tell you that story g equals 1 turns out to be a little boring. So let me take the case of, I'll start with g equals 2. But first let me define a power series. So we already learned from Euler that you should make generating functions. And so for each, and maybe I'll call this just n because it's the one I care about. I'll call this n hat. It's bigger. And so I'll put fg. No, hat is bad. Star. Star is the same thing where I allow also disconnected coverings. But as I said, that's just a detail. OK, so as an example, as I say, g is 1 is kind of boring. There is a formula. Well, actually, it's very pretty. And what you get is log eta. But I don't want to go into that. But for g equals 2, what you get is, so f2 turns out, well, there can't be a covering of degree 1, because if it's degree 1, the things would be isomorphic. So the smallest degree is q squared. And this time, they're all integers. That's actually kind of exceptional. Plus 8q cubed, plus 30q to the 4th, plus 80q to the 5th, plus 180q to the 6th, and so on. But as I said, in general, this is quite exceptional for genus 2. If you take genus 3, for instance, the corresponding numbers are, again, it starts with q squared, but now it's a 12th because of some funny way we're counting. And so the theorem, which is a combination, I'll just put Dijkgraaf because that's, I think, the main person on the physics side who found this. So he found it, but it wasn't a completely rigorous proof. It used, for the second part, sort of road path integrals, quantum field theory. And then Kaneko was here last week, and I proved it in the same year and in the same volume. And Dijkgraaf showed it, and we found a rigorous proof. And the wonderful theorem, I think it's wonderful, that Dijkgraaf discovered is that this thing is a quasi-modular form. And because of what I told you, then we know it on the nose. You just look at a few coefficients. So for instance, f2 is just, well, I mean, I don't have it in my head. Actually, I do. I think that, but I forgot. There are only, in weight 6, there are only 3 possible monomers in E2, E4, and E6. It's E2 cubed, E4, and E6. And so you just work out the first 3 coefficients, and that forces these coefficients here. Actually, you don't even need the difficult ones. You just 0, 0, 1. That's all. I mean, these two were trivially zero. Trivial or not, they're true. So those 3 already force. Then all the others you get for free. And in this particular case, you're lucky because we're in such a low weight. You can also write this, if it makes you happier, as E4 prime. Remember, my prime is without the 2 pi I, plus 10 E2 triple prime divided by, is that correct? 4 and 2 is 6. 2 and 4 is 6 are just 2 primes, divided by 1,440, and that actually implies a closed formula that in the case of genus 2, this number is n over 6 times the sum over all divisors of n of d cubed minus d squared, dn. It's just that. Okay, so in this particular case, you get a closed formula, but in general, you won't. Okay, so that's an amazing thing, but it seems like I've strayed totally from my topic because suddenly I gave you a nice application, at least I hope you think it's nice, of quasi-modular forms, but in a completely different field from finite group theory, because here I'm talking about ramified coverings. But actually, it's known, and it was very well known, this goes back to at least Horvitz, that to solve such problems of counting coverings is a pure problem of group theory. And it's a problem of the group theory of the symmetric group, because the symmetric group will permute those n things. So we have these n branches, but then two of them are coming together. And so that means that we have the symmetric group, but we also have the transposition. Remember, I had it for n equals 3, but you have it for every n, which is the class where you just interchange two things and keep everything else fixed. That's a well-defined conjugacy class, and that is called the transpositions, and that's the one that will play a role in a second. Yes?
How are you counting the coverings to get rational numbers? What do you
I
do?
said it's what you always do in all of mathematics, 1 over the number of automorphisms.
Okay.
But I don't want to say what automorphisms are because you have to fix ramification points and so on. It's really better left unsaid. But the reason there are denominators is because if a thing has 6 symmetries, you have to count it as 1/6. But to define carefully what a symmetry is, I can try to do it. I'll even get it wrong privately, but I don't want to try to do it in public. Okay, but that's the reason that you can get denominators and indeed do. So let me just say briefly how you reduce this to a problem of number theory. So, and this is really very, very pretty. So this is what Descartes did in this particular case. So what he actually proved, but using group theory, and I'll show you in a minute where this came, is that you start with this following. Well, this is going to be completely unmotivated now, because I didn't tell you as I was going to the Jacobi triple product formula, but just believe me, here's 1 minus q to the n. Remember, q is e to the 2 pi I tau. And then I have the product over n, again positive, but this time sort of fermionic positive, so half integers, so half 3 halves. And then I take 1 minus e to the n squared x over 2, q to the n zeta. Zeta is e to the 2 pi I z. And remember that q is e to the 2 pi I tau. And then you do the same with sort of a few signs changed, minus n squared x over 2, q to the n zeta inverse. So now this is the procedure, he said. Now you go to theta 0 of just x and tau, which is the coefficient. It's the constant term in this as a Taylor series. It's the coefficient of the zeta to 0. You multiply this out on your computer, and you can do that. And then you find the sum. Well, it's got an expansion, so you expand it. It's got an even expansion. That's very easy to see. And then the claim is that if you take this generating function that I talked about here, but I wanted the one with the star for non-connected coverings, then that is exactly a index, I guess, g minus 1 of tau. So the real theorem is that a n of tau is the quasi-modular form of weight 6n. So here it'll be 6g minus 6. And then the last step is that you take the logarithm of this. So this starts with 1, a1, etc., a1 x squared, and so on. So this is the same as by what I just told you, is f2 star. And now you take the logarithm of this, and then you'll get f1 x squared plus, f2 plus f3 x cubed, and so on. So the recipe that Descartes gave, I mean, I've just given it for completeness. You take this infinite product, then you take the coefficient of zeta to the 0, then you expand in powers of x. You get a power series starting with 1. When you take the log, its coefficients are the fn, and if you don't take the log, they're the coefficients where you allow non-connected coverings. But the reason for that, from group theory, well, I'll now come to it. So we proved this, as I said, Kaneko and I, rigorously, and then it was generalized by Bloch and Okunkov, and it's very, very nice. I'm going to, since the time is running out, I'm going to skip a little bit of the next explanation and just cut to the chase, as they say. So I certainly don't need the monster group anymore. This is not easy. Okay, so it turns out, so let me do the following. Let f be a function of partitions. Now remember, I showed you the partitions at the beginning. For instance, for 3, it was 1, 2, 3, or if you want 1 plus 1 plus 1, then 1, 2, 3, so 2 plus 1, or 1, 2, 3. And you can represent this just by making a picture where you show the size. This is size 1, this is size 1, this is size 1, so you get a diagram like that. Here you have one of size 2 and one of size 1, so you get a diagram like this, and here you get one of size 3. So these are called Young diagrams, and they're simply, you simply have k squared, if k is the longest, biggest thing in your partition, you put k squares, and then the next number of squares, and so on. You make such a picture. Okay? Now, let's say that so this will be called a partition. So any way that I do it, a partition of 3 might be 1 plus 1 plus 1, 1 plus 2, or 3. So we have a partition. It's written usually like this, and then you write that n is the size of the partition. So if I give you the partition 1 plus 2, then n is, not surprisingly, 3. And so now if you have a function of partitions, I'm going to do something with that in a second, I'm going to make an average, which is just like what you do in statistical mechanics or in quantum field theory. So you have a partition function, which is, you simply count every possible state, which is all possible partitions, but with a weight, like a Boltzmann weight, so tau is something like the temperature, the inverse temperature, and it's q to the size of the partition. Well, we know what that is, because the sum lambda q to the lambda, well, each lambda is a partition of some number. And so you have q to the n, but the number it's a partition of has p of n partitions. And so this is exactly our old friend, which we already know is a modular form. So the denominator up to the stupid q to the 1/24th is 1 over eta, which means I'm multiplying by eta. And then upstairs, this is meant to be an average. Well, of course, you put f of lambda q to the lambda. Okay? Well, then I'm going to now show you a nice example. So here's an example. Remember, we had this function chi v of c for every conjugacy class, and then I did another one I called uv of c. So in particular, I can do this for the transposition. This is, remember, this class that you have for every n, where you interchange 1 and 2 and leave everything else the same. You interchange 2 points. So this new v of t is a well-defined number, and remember, v corresponds to a partition, because there's a bijection, actually, I didn't tell you that, between partitions and not only conjugate class, but also representations. So every partition I have this new lambda of t, and so in particular, I can take this new lambda of t, and then the group theory argument, so this is essentially Hurwitz. I mean, it's taken up, but using an argument that goes back to Hurwitz. In this particular case, you take as a function you take this function. So a function on partition, certainly this number, nu lambda of t, is such a function, and so is its 2g minus second power, and the claim is that its average is that, and that formula, if you multiply it out, gives you this mysterious thing. And I'll show you that briefly, because I won't show you a gorgeous generalization, and for that I need slightly more information. So you can almost, with what I'm about to tell, you can almost go from this formula, which is essentially Hurwitz. I said that's a simple group theoretical argument, how you count coverings. You can go from this formula, which looks elementary, to that one, which looks kind of wild, in a very simple way that you'll almost be able to see in a second. But anyway, so the theorem that Kaneko and I proved, what Descartes had predicted, was this. So let me be slightly more general, and this is really, really pretty. So this is now something for, I hope, for everyone, even for the experts. So here's an example of a function on partitions. So the partition, remember, corresponds to it's on a partition or conjugacy class in the group partitions. So I can write it as lambda. You can think of it as a Young diagram. And I'm going to have functions p nu of lambda, where nu is 0, 1, 2, and so on. And just as examples, p0 of lambda will always be 0. P1 of lambda will always be n, the size, which is the thing it's a partition of. And P2 of lambda will be exactly, well, it's 1/2 this, or 2 times, excuse me. It's 2 times this new lambda of the transposition class. So up to a factor of 2, and actually that, no, I think this is correct. So let me tell you what it is. And for that, there's a wonderful bijection. So let me define a balanced fermionic set. Isn't that a cute word? I invented it. A balanced fermionic set, BFS, is a set of half integers. So that's the fermionic part. A finite set, such that the numbers, every not half integers, either strictly positive or strictly negative, I want equally many positive ones and negative ones. Okay, so you can easily imagine such a set. And now I'll show you that there's a bijection with partitions. Well, if you have a partition, so here are maybe some of the pieces of the partition, then you take the Young diagram, which we had before, and let's say it's, I don't know, it doesn't really matter what example I take, because every example works. That's the nice thing about true theorems. So you take your Young diagram. This is particularly, that's just what I want to avoid. It's a stupidly symmetric one. Let me make it a little more interesting. So here's a Young diagram. Remember, the outside of this is a Young diagram. You take the diagonal, and then you see here this has area 1/2. This is area 1, 2 1/2. So it's 2 1/2. This is area 1, 2, 3 1/2. This is area 1/2, 1 1/2, and probably 3 1/2, depending. I did it, and so my balanced set would be starting at the right, at the top, 3 1/2, 2 1/2, 1/2, and then the others I put with a minus sign. And obviously there are equally many belows above because they share the diagonal, and this is obviously a bijection. So these balanced fermionic sets are that, and this p nu of lambda is simply you sum all the elements of your balanced set, c to the nu, except for two little things. First, you put in a sign. And secondly, for a reason that's very amusing but that I won't have time to explain, you subtract a multiple of zeta of minus nu, which is that same Bernoulli number we saw before. But it's anyway, you subtract some constant depending only on nu. So let's do the three cases I had. If nu is 0, then this correction is 0, because there's a 0 in front of it. And so here you have the sum sine of c times c to the nu. That just is the number of positive minus the number of negative. So it's 0, because they're equal. It's balanced. If nu is 1, the sine of a number times the number is just the absolute value of the number. And of course, that's the total area of this Young diagram. So that's the n. And finally, it's easy to check that this thing is also true. So now the wonderful generalization by Bloch and Okunkov. So this was, I think, 2000. Our paper, as I said, was 1995, both diagraphs and ours, was that if you take any product of these p nu's, some finite product, and you make the corresponding q average, then this will always be a quasi-modular form, and the weight, this thing is weight 2, this is weight 3, the next one is weight 4, and so on. So in particular, you see that in the case I had before, this new lambda of t up to a factor of 2 is the same as p2, so I have p2 of lambda to the g minus 1, and so I get, so that's 3, except that no, it's 2g minus 2, so it's 3 times 2g minus 2, it's weight 6g minus 6 as it's meant to be. So that's the absolutely wonderful generalization. It's already a few years old, and I'm currently doing some work with Mathematik-Müller coming from dynamical systems, which generalizes that. So now I have 0 minutes, but I think I started a little late, right? I was introduced, and all kinds of things happened at the beginning. I told jokes. So let me do part 3 in, okay, no more talking slowly. Okay. So the last is what are called mock modular forms. So this is a famous story in the history of mathematics. Ramanujan, the Indian genius, wrote a letter in 1913 to Hardy saying that he'd done all these wonderful things. Hardy invited him to England. They collaborated for years. Ramanujan went back after World War I ended, was very depressed, and died 2 years later. He became ill in April 1920. But 3 months earlier, he sent a letter to Hardy where he said he'd discovered a wonderful new class of objects called Mach theta functions, and he gave many examples, and I was going to give one from his letter and explain a little, but I'll just say that Ramanujan's Mach theta functions, so Mach for him simply meant not true, but very near. So a little like my quality before, and theta function for him didn't mean what it means for us, but simply modular form. So these were things that behaved nearly like modular forms, but didn't quite, but he didn't know what the definition was. He certainly didn't give it. And it was only, this was 1920. As I said, January 1920. And the enigma was only resolved by my graduate student, then graduate student, Sander Zagier in Utrecht in 2002. He found a mathematical definition of a big class of functions that we now call mock modular forms that includes these 17 examples. So he gave 17 examples, but there are more. And one in particular is the one I'll talk about, and I'll just say very, very briefly what it means to be mock, and then say the point, and then I'll stop. So it has, remember we had eta, and actually we had eta inverse, which was the partition function of the generating function of partitions. So those were integers, but because of the q to the minus 1/24th, there was one negative power, q to the minus 1/24th. Well, here you have something very similar. You have q to the minus 8th, and the first coefficient is minus 1, plus 45q, plus 231q squared, plus 770q cubed, and so on. So this is a new example, not one of Ramanujan's. I'm not sure if in any of his unpublished notebooks there's one. I think there are some that are equivalent to this in that they differ from this one maybe by ordinary modular forms. I'm not entirely sure. But this thing is an example, believe me, of a mock modular form of weight a half. And let me tell you just in a word what that means. Remember that a quasi-modular form like E2 meant that you started with your Q expansion, so that's a holomorphic function of power series in Q, like this one, but then you added to it. In that case, it was really easy. It was the sum, in that case, it was the sum 1 over y. It was just 1 over y in the case of E2. Here it's more complicated. You take Q to the minus n squared over 24. There's some factor, there's some sign, and in front of it you have the error function, complementary error function of, I think the argument is the square root of pi y over 6 times absolute value of n, and then there's a sign and some other thing. So you correct this thing by completely explicit, very rapidly convergent sum, completely elementary. There's no mystery here. The coefficients here are all 1 or 0, but you have to add this explicit correction term, and that's why it took almost a century to discover, because it's very far from obvious. And then this thing is not holomorphic, but this one transforms like a true modular form, like a modular form of weight 3/2. Okay? So there's a specific recipe for that. The thing, I mean, I can tell you just very, very briefly, since it's non-holomorphic, the non-holomorphicity, the piece you've added, is detected by applying the Cauchy-Riemann operator, d by d tau bar, because if it were so that would kill this part, and then all that's left is this, and what you get is y, I think, to the minus a half, maybe plus a half at a constant, and then in this case it's 8 of tau cubed, complex conjugate. In other words, the thing that you've added is just a simple integral of a known modular form, which is in this case is 8 of tau cubed, and you've integrated once. You've added something whose derivative is a known function. So that's very easy. It's simply this one, you've integrated once a modular form, but it's a non-holomorphic thing because you put a complex conjugate there and a power of y. And so it's a little mysterious. Now this particular one actually was not discovered by the mathematicians. It was discovered by the physicists. Several people, Eguchi and Taormina, who's now in Durham, and then a paper a year later, this was 1988 and 1989, the two of them, and Yang and Oguri, and they discovered it in connection with the superconformal, with the representations of the superconformal algebra, which I now know what it is, but the non-physicists probably don't, in n equals 4 superalgebra, and you decompose the elliptic genus of a K3 surface into those things, and these coefficients emerge. So they'd actually found that, but that was long before this formal definition by Zagier had been given in 2002, and so after that the thing was sort of rediscovered. But then in the end, 3 mathematicians, 2 of whom were of those original authors, so they certainly knew that work very well, Eguchi, Oguri, and Tachikawa, made an absolutely sensational discovery in 2010. And to me, the most amazing thing is that it's not better known by pure mathematicians, because the physicists got very excited, and some pure mathematicians, but it somehow didn't become nearly as famous as the moonshine story, which became a sensation overnight. They just opened a table of, the atlas of finite groups, looked at the tables of dimensions, and they discovered that if you played the same game that McKay had done with the J function, and he found the dimensions of the first few irreducible representations of the monster, except they were slightly off. Here, they found these numbers, actually all 3 of them, if I remember, on the nose, with no addition in this case, are the dimensions of low-dimensional irreducible representations of the group called M24, the Mathieu group of order of index 24, which is not as big as the monster, but still a very big group, and one of those famous 26 sporadic groups. So just to summarize, 2 years ago, there was a spectacular breakthrough. It was conjectural at first, and now there are dozens of papers around it, many, many connections with other parts of mathematics and physics. But there's a new moonshine story in which the role of the monster is replaced by this simpler, and you could say duller group, the Mathieu group of order 24. But to make up for it, the role of the J function, which was a weight 0 classical modular form, is replaced by weight 1/2 Mach modular form, this new class of objects that grew out of solving the mystery of the Mach theta functions of Ramanujan. So I think I'll end with that, having used up my time by any standards.
Well, thank you so much for that
virtuoso formulas, if I may say so. Will you take some questions?
I hope there will be some, yeah.
So the monster group is symmetries of something. What about the Mathieu group?
Well, as you know, that's true, but it took a few years to find that out.
Yeah.
So in the story of the moonshine, McKay found it in 1978. Then it was several years later, I don't remember the year, when Frankel, Lepofsky, and Merman constructed a huge module, graded module, of which acted as symmetries, and then the precise moonshine conjecture became that the dimensions of those pieces were the coefficients of J, and also the traces of the other conjugacy classes of the monster on those pieces were other modular forms. And when I wrote that huge order of the thing and didn't tell you what the primes were, the last few were 47, 59, and 71. That list of primes was also recognized, I think also by McKay. They're exactly the primes where the group upper half plane modular gamma 0 star of P has genus 0. And so those were exactly the hot modules. There was a whole wonderful story. And then Borchertz proved it in 1992, but that was 15 years later. So give these guys time. As I said, there are hordes of people working on it. There's a wonderful collection of papers. Well, there are many people. Anne Tarlin and Kathleen Wendland is one group, but I'll mention more. Miranda Cheng, John Duncan, and Jeff Harvey. I saw two of them just last week in AIM. We had a meeting exactly on counting things in algebraic geometry, so Gromov-Witten invariants and the like, and modular forms. And this was one of the key examples because this is actually very close. So there's also a relatively new paper by Samir Murti, it's not alphabetical order, Atish Dabholkar, who's a very well-known string theorist and gravitational theorist. Originally this is postdoc, Samir Murti and myself, 150-page paper of last year, which relates Mach modular forms, and in particular ones of low index, whatever the index is, with the string theory of black holes. And so we found in this thing really coming from counting states in a certain model, counting BPS states, we found in particular very, very special modular forms of which, well, they were numbered H1, H2, and this is, for instance, H2, and some of them were particularly special in our story and played a special role. And in their story, they also find some special ones that are connected with finite groups, and it's the same collection. And so they, and as I say, many other people are looking for H2. It's connected with K3 surfaces and the automorphisms of K3 surfaces. They're looking very hard. There's a lot found. I just heard a beautiful lecture by Rhonda Cheng a week ago, and she found that there's a correspondence between these very special Mach modular forms and the 23 Niemeyer lattices. Niemeyer showed that there are 24 lattices of dimension 24, one of which is the Leech, and the others have a root system. I think 15 of those root systems contain an A1, an AI, and those 15 exactly give their special Mach modular forms, and it's a miracle, and they also give ours, except that one is missing on our list. Nobody knows why. It's not because we overlooked it. It doesn't quite fit. And so, although in the same paper, I gave an example that I said we have 3 examples with square-free M, and they were 6, 10, and 18. And it was just pointed out to me last week that 18 isn't all that square-free. But anyway, but we didn't overlook 12, which was the missing one. So there's a series of mysteries, and indeed your question is just spot on. That's what they're looking for, is objects that have the Mathieu groups, their symmetry. There are some, there's a whole saga about this. I'm not a K3 person, and also I think they aren't finished. But they're hard at work on it. If you just go to the archive and type any of these names, you'll start finding absolutely beautiful, unreadable papers. Other questions? Maybe a more elementary one. Not quite such an expert as Ezra. No naive questions?
Yes, Don. Can I multiply E4 by E2 on the bottom line of the top equation?
In the bottom line of the top equation.
Top line of the bottom equation.
Yeah. On the left-hand side.
18, it turns out, is not square-free, and E4 does not have weight 6. Thank you very much. You not only can, but you absolutely should. I apologize. Yes, thank you. That was a very discreet way of pointing out a mistake. You're more than entitled to perform that multiplication. I thought you were asking something else. You can multiply E4 by itself, and something nice happens. As I told you, it's E8, well, the multiple of G8. And I thought you were asking, can I multiply E2 by E4 and get something nice? And the answer is, in fact, yes. What you get is E6 plus the multiply, I think it's 12 in this case, times E2 prime, the derivative, defined the way that I did. So you can multiply them, and that's another completely different way of writing it. And actually, that's how I got from one of these formulas to the other. But of course, it's supposed to all have weight 6.
E4 prime. E4 prime, no?
Sorry?
E4 prime?
That's a 4, and this is a 4. Okay, and 18 is square free. Yeah, I mean, I'm sorry. It's never happened to me before to make a mistake, and now I've just gone and made 2.
Another one. I was going to ask a naive question. There you said that those coefficients match the size of the irreducible representations of the Matthew group. What if you leave off the 744 for the in J?
But the 740, you see here, it's very striking that there is no 744 here. There's no constant term, right? Because this is not q to the 0, it's q to the minus an eighth. And that's not q to the 0, it's q to the 7/8. This has no constant term. This had a constant term. The constant term is essentially meaningless. I said when I wrote it down, I said, well, there's something about 3 times the dimension but it's not really because of j, it's because of the cube root of j. This term is meaningless because if j is a modular form, there's nothing very special about E4 cubed. It's just a random modular form. Every modular form of weight 12 is a combination of E4 cubed and E6, or if you prefer, of E4 cubed and delta. So an equally good choice is this. The only canonical thing is the denominator. So I can perfectly well renormalize. So this coefficient you cannot expect to have a meaning. It's man-made. Now, having said that, turns out it's actually not true. There is a canonical choice, but it's not 744, it's 24. And this was Atkin who discovered, and he had 4 different arguments. And 2 of them I can give you right now. One is which thing should we take at weight 12? Upstairs. Downstairs it's delta. Well, there's only one canonical thing. It's the theta series of a lattice, but there are 24 lattices, and only one is everyone's favorite. It's the Leech lattice. But the Leech lattice, by definition, has no vectors of length 2. So this one starts with the coefficient 0. Q starts with, delta starts, as I wrote several times, with the 24, and so it starts with the 24. But there's even a better argument. Rademacher gave an explicit formula for this, or for every Cn. Cn, the coefficient of Qn, is some sum like the one that I gave for Pn. Remember, it was e to the pi squared of 2n over 3. There's an absolutely similar form with infinitely many terms, and it's convergent, and it gives Cn on the nose. And his formula for n equals 0 simply gives 24. That's a message from on high that the coefficient really is 24. So in fact, it's not quite true that it's arbitrary. And then you could reasonably ask, so what's the 24? And then the answer is, I don't know. Okay. But the 744 has no particular meaning in this context. I mean, the 24 is, of course, the Euler characteristic of K3 surface and lots of other things, but I don't know which of those is playing a role here.
Okay. I think the magic must stop, and you must go and have a glass of wine to recover from
That sounds like an excellent idea.
evening. Let us thank Don very much for that.
Thank you.